Okay, very good morning once again.
Good afternoon, sir.
Yeah, good afternoon. A very good afternoon, please. So I think we can begin. So just before we begin, do we have any questions so far? So we could resolve any doubts before we go on. Okay, okay. I think we'll just jump right
No, sir.
Good sir.
afternoon, so we can go on. Okay.
Good sir.
Hello? Go ahead, please.
Yeah, there's a pending question from last class regarding the energy signal. Discrete, how to determine if a discrete time signal is an energy signal.
Yeah,
And
yeah.
I asked you the last class. You said because of time, you cannot answer. So I
Oh,
want to bring up the question again.
okay. That sounds good. So I think we are going to attend to that because after this, I'm going to go into discrete time system. So I think then we'll be able to establish the background for the discrete time systems and then solve the problem. What do you think?
It sounds good, sir.
Okay, yeah. So because we have been on continuous time signals and now we want to talk about systems, but afterwards we're going to delve into convolution. So as we begin to address the convolution system, then we will now address a few details, okay? Okay, does that sound satisfactory or?
It's okay, sir. You can go on.
Okay then, yeah. Okay. Now, when we talk about systems, we've been able to establish that given a system, once we feed it with an input, then it processes the input, then gives us an output, right? So
Yes, sir.
I think now we want to describe the properties of a system. Now, we already mentioned that a system could either be continuous time or a discrete time system, okay? And if we now have to probably describe, say, the properties of a system, then we want to mention if it's a static system or a dynamic system, okay? And if it's stable and all of that. So in terms of addressing the basic properties of a system, before we now delve into LTI system, to now see, well, what we play with in practice, are they actually LTI systems or not? So I think we'll try to address all of those details. Then afterwards, we'll now go into probably convolution. So where we'll be able to detail the discrete convolution, how the discrete system works, then I think at that point, we should have been able to build sufficient background on the discrete system, which I know I haven't really mentioned. So how do we represent discrete signals? I know I mentioned that in the first class, but how do we now process discrete signals? So I think when we get into that, then we'll begin to play with a couple of activities, okay? Okay, so let's okay, the system types. So we already pulled off continuous time system. Then also pulled off discrete time systems. So continuous time systems are systems that take in continuous signal and feeds continuous output. And discrete time systems are systems that take in discrete signals and then processes it and gives off and produces the discrete response. Then we have static systems. Now, the idea about a static system is that once we feed in a system with, say, an input S of t, we are expected to get Y of t being the same as S of t, such that at that given instant of time, the output should be equivalent to the input. So it means that the output only depends on the present input. So if we consider at, say, S of t at -1, then Y of -1 should be the same as S of -1. Okay? So at time t equal to 0, then Y of naught should be the same as S of naught. And at time t equal to 1, then Y of 1 should be the same as S of 1. So it means that the present output is strictly dependent on the present input for us to have a static system. But for a dynamic system, it means that this system is such that the present output depends on the present input. It also depends on the past input, and it could also depend on the future input. Okay? So it means that Y of t could be the same as S of t plus S of t minus 1. It could be the same as, it could be S of t plus S of t plus 2. So this is past input, this is present input, this is delayed, you know. So what we are trying to say is that at some point, we should be able to identify whether a system is either static or dynamic. Is that clear?
Yes, sir.
Okay.
Yes, sir.
Now, these are two broad categories. So we now want to go into systems that may model what we play with in real life, say causal systems. Now, I'm going to ask a question shortly. Causal systems. Now, these are systems whose present output depends on the present input and or the past values of input. So it means that a causal system could either be dynamic or static. But what is the difference between a causal system and a dynamic system? So can someone tell us?
Yes, sir. For a causal system, it could either be just static and it could either be also dynamic. But a dynamic system cannot be, let's say, static.
Well, no, now I didn't ask between static and dynamic, causal and dynamic. What's the difference between causal and dynamic systems?
The causal system can't depend on future inputs.
What did you say?
The causal system can't depend on future inputs, unlike dynamic systems.
Oh,
Question, do you have 212 today?
perfect. Now, that is the point. Now, although causal systems are dynamic systems or could be dynamic systems, all dynamic systems are not causal systems. Okay? Because in considering dynamic system consists of the component that describes the static system as well as future and past inputs. But for the causal systems, they can only depend on the present and past inputs, not on future inputs. So it means that a causal system could be static. Say y of t is the same as s of t. Now, this is static, but it's a causal system. Now, a causal system could also be the same as y of t be the same as s of t plus s of t minus 1. So meaning it depends on only the past input and present input, but not on future input. Okay? So I can see one hand. Ehis, go ahead, please.
Excuse me, sorry to take you back, but can you go over the definition of static and dynamic system again?
Okay. Now, a static system is a system whose present output depends on present input. That is static. Is that clear?
Yes.
Now, for a dynamic system, the present output rather can depend on either present input, past input, or future inputs. Okay? So the difference between the static and the dynamic system is such that the dynamic system must either depend on past or future input alongside present, but the static system depends only on the present input. It does not depend on past or future inputs. Okay? Is that clear?
Yes, sir. Thank you so much.
So in this case, this is a static system. This is a dynamic system because this depends on present input, but this is a past input. How do I mean? So let's assume for this y of 0, you see that this will be s of 0 plus s of minus 1 when t is 0.
Sir, I can't hear you.
Really? Can others hear me?
Yes,
Thank you,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So probably you want to check your device if you turn down the volume of your device, okay? So I can see one hand up, Ibrahim.
Okay, sir. Is it possible to have a dynamic system that only depend on the either future or the past signal?
Why not?
Why not?
That's what makes it dynamic. The bottom line is it depends on either past or future input. Now, a dynamic system could be y of t
This one should use it.
be the same as s of t minus 2. It could also be y of t be the same as s of t. So in this case, at y of 0, the present, then this will be y of minus 2. Why this will be y of 0 same as s of. So why this is dependent on past input,
Ibrahim, keep off your mic. There's feedback.
present input. Is that clear?
Yes, sir.
Okay. So this describes static system. Okay. But this is a dynamic, I mean. This describes dynamic system because it could depend on either past or present or future inputs. But this depends strictly on present input. So if y of 1 is going to be s of 1. Now y of 2 is going to be s of 2. So this output depends on present input. So this is strictly static. Okay? But in this, now this is not a causal system because it depends on future input. Okay? But this is a causal system because it depends on past input. So when the system depends on either present or past input, then we say it is a causal system. As we progress, you realize that we have so much interest in causal systems. Okay? The reason will become clearer as we move on. Now, we also have non-causal systems. Okay? So in this case, the present output depends on both the past, the present, and future values of the input. Okay? So in other words, y of t in this case is the same as s of t plus s of t minus 1 plus s of t plus 1, for instance. So this is present input, this is past input, and this is future input. So if, for instance, we have y of 0, so it's going to give us s of 0 plus s of minus 1 plus s of 1. So this is a non-causal system. Okay, we have one hand up. Ibubechuku, go ahead, please.
Yes, sir. Thank you, sir. For a non-causal system, is it compulsory it depends on both present, past, and future inputs?
Beautiful. Now, it may, not necessarily. Okay? But the fact that it depends on future input makes it non-causal.
Okay, sir.
Okay. I'm sure that is clear, right?
Yes, sir.
Now, we now have the anti-causal systems. Anti-causal system. Okay, we have Kelvin. Go ahead, please.
Uh,
Thank you, sir. What is the difference between a non-causal system and the non-causal system and the dynamic system?
Yeah, a non-causal system is a dynamic system because it is non-causal largely because it depends on future inputs. Okay, that is what makes it non-causal. Now, if it was dependent on only the present and the past inputs, it would be causal. Okay, but mind you, causal systems are dynamic systems. All dynamic systems are not causal systems because some dynamic systems are non-causal systems, largely because they show some level of dependence on future inputs. Okay, but we also have systems that depend strictly on future values of input. We call them the anti-causal systems. Say y of t is the same as s of t plus 1 or 2, for instance. So this is strict, it's also a dynamic system, but it's strictly dependent on future inputs. So it is not a non-causal system, but rather it is an anti-causal system. Daniel, go ahead, please.
okay. So the question: this anti-causal system can they also be known as non-causal system, or there's a difference between them? And that non-causal system, can they also is it also a name of dynamic system, or is it different?
Okay, now I mentioned that earlier. They are all dynamic systems. Causal,
Okay.
non-causal, anti-causal systems are all dynamic systems. largely because they depend on some input values other than the present input value. Okay. Did you get that? Now the fact that they not only depend on the present value of the input makes them dynamic systems. So if the system is such that the output depends strictly on the present input value, it is static. So it means that once I feed this input at this instant of time, I get my output relative to that input value. But now that the system depends on values of input that may not necessarily be the input value at that instant of time, makes the system dynamic. But the point is, all non-causal systems are not anti-causal systems. Okay? So we need someone to mute the mic. There's so much background noise.
So please repeat what you just said. I didn't get that.
Okay, I just said that all non-causal systems are not anti-causal systems. Okay, let's put it here in red.
Okay, sir.
All non-causal systems are not anti-causal systems because the anti-causal systems depends only on the future input value. But non-causal systems depends on the future values of input and may also depend on the present or past input values. Okay, so we can as well classify anti-causal systems as non-causal systems. The same way we are able to classify your causal, non-causal, and anti-causal systems as dynamic systems. But yet we now say that all dynamic systems are not causal systems. So all anti-causal systems may be classified as non-causal systems because they depend on future values of input. But all non-causal systems are not anti-causal systems because should the non-causal system depend on other values of input, probably the past and the present alongside the future values of the input, they cease to become anti-causal, but they are non-causal. Is that clear?
Yes, sir.
Okay, so we have Dejo. Go ahead, please.
Good day, sir. Can you hear me?
Yeah, I can hear you.
So, my question is, you said there are static system and there are dynamic system. When you started explaining it, you made an example, but I just want to get this straight. A dynamic system can have a static component, but cannot be a static system. Yes or no?
A dynamic system, yeah, a dynamic system can have a static component, but it must have the dynamic component to make it dynamic. And what makes it dynamic is that it depends on some input values other than the input value at that instant of time.
Okay. Thank you, sir.
You're welcome.
So I just wanted to get that.
Yeah. That's fine. That's fine. Okay. Now that we have described all of this, okay. Someone is singing. Please get your mic. Oriako, go ahead, please. I can see on
I wanted to ask if these are non-causal and anti-causal, if they are just like
hold on, please.
of dynamic.
I think there's background noise. Someone is singing. Can the person mute his mic? Okay. Let the person so we're able to hear you. Okay. Okay, go ahead.
Good afternoon.
Yeah, good afternoon, Oriako.
Please, I wanted to ask if this causal, non-causal, and anti-causal that we are doing are like subcategories of dynamic systems.
Okay, can we say there are subcategories of dynamic systems? They are examples of dynamic systems. Okay, but if you say subcategory, I don't know. I really don't know what you mean by the word subcategory. So except you want to explain what you mean by subcategory.
Like maybe they're like types of dynamic systems. That's what I meant.
Yeah, that's what we mentioned, that, you know, causal, anti-causal, non-causal systems, largely because they depend on input values that may not have necessarily occurred at that instant of time, make them dynamic. Okay? That makes them dynamic systems. Okay. Now, let us move on, because our goal is to analyze linear time invariant systems, okay? So we just need to build the background, which we are doing right now. So we are able to perform certain operations.
Okay, sir. Thank you very much, sir.
You're welcome. So now we want to move on to the next, linear systems, okay? So linear, okay. Linear systems. Now, when we say a system is linear, it means that it obeys the principle of superposition, okay? Now, this will become clearer when you look up the lecture notes on superposition theory or theorem in the Fundamentals of Electrical Engineering playlist.
Sorry. You said linear system depend on. I didn't get what you just said.
Okay, so when I'm talking about linear systems, okay? So linear systems are based, or better still, linear systems are systems whose operation is based on the principle of superposition, okay? And I said, well, you may want to look up the lecture note on superposition theorem in the Fundamentals of Electrical Engineering. Yeah, so then you see how we actually apply the superposition theorem in analyzing circuits. But when we say that this system is linear, likely because it obeys the principle of superposition, then what do we mean? What do we mean? So it means that it actually obeys two fundamental laws. Okay? One is the law of additivity, and the second is the law of homogeneity. Now, when we talk about the law of homogeneity, we actually mean scaling, okay? So if we are given two systems, say S1 of t fed into a system, and here it gives us Y1 of t, and then we have another system such that, or another input, say S of 2t, fed into the same system, and then we get Y2 of t. Now, should we, for instance, add both signals, S1 of t plus S2 of t, and feed them into the same system, then we should get Y1 of t plus Y2 of t, which is, or better still, which describes the law of additivity, okay? Now, the fact that the law of additivity is observed does not make the system linear. It must also obey the law of homogeneity, such that if, for instance, we have a signal, say this signal, S of t, is now fed into a scalar or through a scalar or scaled by some parameter and then fed into the system, then the output should be the same as the product of that scaling parameter and the signal. Okay? And then should we, for instance, feed the same signal into the same system? Okay? And then have our output Y fed into that system where we have the scalar, then our final output should also be the same as the product of the scalar and the signal. So should these two operations give us the same outcome, then we say that the system also have, or the system, better still, the system obeys the scaling law, or better still, the law of homogeneity. And once these two laws are observed by the system, then we say that the system is linear. But the bottom line is, do we really have linear systems in practice? I don't think so. Okay? But do certain systems in practice operate within the linearity parameter? Yes, of course. But when things go wrong, the system may cease to obey the principle of linearity. Take a resistor, for instance. You know by Ohm's law that V is the same as IR. And this shows some level of linearity. Okay? But depending on the value of resistance, this system may become nonlinear because when excessive current flows through this resistor, it could blow out. And when it blows out, then the principle of linearity will not be observed. Then the system becomes nonlinear. So it means that there is the operating point for which linearity is observed in most of our devices. And we want to maintain that level of linearity for us to be able to get the acceptable performance, okay? Except we want to design a system that will operate otherwise. Okay, Love, go ahead, please.
Can you just come again with the definition, with the explanation of the law of homogeneity?
With the definition of what?
The law of homogeneity.
Okay, the law of homogeneity or homogeneity, that's scaling. Now, I know in our last class, we talked a bit of, about scaling, amplitude scaling, you know, this scaling, that scaling, yeah? So that's what we are trying to do here, okay? So we are trying to scale this signal, S of t, through what we talked about, amplitude scaling. And now this is the system, okay? And this is the system, okay? Now, we want to test this system. We want to be sure if this system obeys the law of homogeneity. So what we do is we feed the system through a scalar. So we scale the amplitude. So it means at this point, let's change this color. So it means once S of t goes through this operator, so at this point, we are going to be having Ks of t fed into the system. And once this goes into the system, then Y of t will be the same as Ks of t. Is that clear? I need to hear from Akintoye Love. Is that clear?
Yes, sir, it's clear, sir.
Okay, now, once this is observed, we are good, but we are not still convinced. Let's put it that way. So we want to reverse the order. So we want to feed this same signal into the system so that at this point, we have S of t. So once we take this S of t, so let's change this to S of t. So it doesn't, so say this is our expected output, but it's S of t, right? Once we now feed that S of t into the same scalar that will scale up our signal with some K parameter, and then have the same output as we got previously, then we say the homogeneity law has been observed. Is that clear now?
Yes, sir.
Okay. Now,
Sorry,
what
sir, that when x of t passes through the first system, it still becomes x of t. It does not change or what? I don't really understand that part.
this part? Okay. Now, this system just gave us our output, right? So we fed the signal into the system, and this is what we get. Now, we're assuming that, for instance, that this is a unity system, a unit system, okay? So it's just multiplying. Hello? Tell me.
Sorry, sir.
Go ahead.
I mean, this part under the
this
the
part.
part.
This part.
Yes, that part.
And that's what I'm trying to explain. Now, because when we begin to talk about LTI system, you will realize that, well, the system will definitely have an impact on the signal. Okay, so that's what we begin to talk about, the impulse response, because that will help us. Because when we move from the impulse response in the time domain to the frequency domain, then we begin to talk about transfer function. That is when we begin to analyze the system. Okay, so you should be rest assured that the system must have an impact on the signal. But here we are trying to say, well, this system property is just unity. So that when it multiplies the signal, Ks of t, we are getting Ks of t. But ideally, it's supposed to introduce some parameter, say, h of t, convolving with this process, for which h of t is the system parameter. But we are not going there that mile yet, okay? So we just want to take it in bits, okay? So let's assume that the parameter that describes this system is a unit value, okay? Unity value. It's unity. It's 1. So that once this Ks of t goes through the system, then we are getting this Ks of t. But this time, S of t, this is signal, S of t, this S of t, right? We just took it from the same source, S of t. It comes this way, gets into the system, so the output should be S of t. Okay? Because 1 dot S of t should be S of t. Okay, that's what we get. Is that clear, Elvis?
Yes, sir. Thank you.
But now that is not our final output. We still have to scale it. So we just got the output from the system. Then we now pass it through a scaling parameter. And then we now got the same. So you observe that the output in both scenarios is the same. So it means that the law of homogeneity is observed. That's what we're trying to say. So once this is observed, both the law of additivity and law of homogeneity are observed, then we say the system is linear, largely because it has obeyed the principle of superposition. Because for this principle of superposition to be satisfied, then these two laws must hold. Is that clear for linear systems?
Yes, sir.
Okay. Now,
Yes.
if that is clear for linear systems, then we now talk about non-linear systems. So the idea about nonlinear systems is that the principle of superposition is not obeyed. So it means that if we feed a system x1 of t plus s2 of t, feed the system, then y of t is not going to be the same as s1 of t plus s2 of t. Okay? So it means additivity is not observed. And also, when we have a signal fed into a scaling parameter or a scalar, k, and then the output is fed into a system, and then y of t being the output is not the same as ks of t, then we say homogeneity is not observed. So when we have a system whereby either of these two laws are not observed, we say it is nonlinear. And you now see that, fine, we try to figure out the operating point of a system where we can assume linearity. Okay, so when we talk about optical communication and the likes, we want to assume, we want to look at the linear domain for transmission, where we'll come to all of those in application. Okay, so because we have to, we end up dealing with a whole lot, you know, when the system becomes nonlinear. But we also need nonlinear systems. They have the applications. So we now have time invariant systems. Okay, time invariant systems. Time invariant systems. So we've mentioned this over and over again. Okay, so it means that any time shift, be it delay or advance in the input signal, will cause an equivalent time shift in the output. Okay, so it means that if, for instance, the input is delayed by some parameter tau and fed into the system, then the output should also be delayed by the same amount of delay. Now, what if the signal is advanced by some time tau, then fed into a system? Then the output also should be advanced by the same amount of time tau. So in other words, in this case, there is no time scaling. Okay, no time scaling. So such that the coefficients must be constant. And then any added or subtracted term other than the input and the output must be zero or a constant. Okay, then we'll say that the system is time invariant. How about a time varying system? So for the time varying system, it means that any time shift in the input may not necessarily result in an equivalent time shift in the output. Okay, so we have systems, for those of you that are into aeronautics, space science, space science or engineering. You observe that, for instance, when you launch a rocket, as it burns large amount of oil, the mass of the rocket begins to reduce quickly over time. Okay, so it means that it is time varying as it propels into space. So, you know, so an example of a time varying system is rockets. Okay, so, and we have quite a bunch of other examples and all of that. So in case you want to you know, play with some of those systems. Yeah. Now, well, our goal is to play with LTI systems, linear time invariant systems. So we know what linearity is. Then we've talked about causality. Now we want to talk about stability. Okay. Now, this another important metric, because when we begin to talk about transforms, we are going to talk about stability. Okay, we'll talk about the region of convergence, and then stability, because we need stable systems actually, you know, to perform useful operations. But do we also need unstable systems? Yes, it depends on the application we are trying to drive. Okay, so the idea about signals and systems is that everything is useful. Everything is just too good for application. So it depends on what you want to drive. Okay, so it's either you want to drive this or that, but depending on the specific application, then we can now begin to look at the system properties we should model to drive that behavior or that pattern. Is that clear, please?
Yes, sir.
Okay, so now
Yes, sir.
let us look at stable systems. So when we talk about stable systems, the first thing that comes to mind is Bible. Okay, so bounded input, bounded output. Okay, bounded input, bounded output. So when we say bounded input, we mean the amplitude is finite, okay? So here also the amplitude is finite. So something like a unit step function, okay? The amplitude, unlike a ramp, the amplitude is extending to infinity. So this is not a stable system. So this is unstable. Okay, so here we can tell where the amplitude is say 2. So we are certain. So we can consider this to be a stable system. So when the input is bounded and then the output is equally bounded, then we say it is a stable system. What if the input is bounded and the output is unbounded? It's unstable. That system is unstable. So both input and output must be bounded, okay, for us to have a stable system. And it means that the amplitude of the input and as well as the amplitude of the output must be finite. So let us consider the system. Let's assume the input fed into the system is a unit step function, okay? So let's say we feed the system that is an integrator. So from negative infinity to t with a unit step function, okay? So what is going to be the output? So it means that y of t, let's change the color. It means that y of t will be the same as integral negative infinity to t u of tau d tau, right? And we already know once we integrate a unit step function, what do we get? We get a ramp, r of t, which is this. So it means that this system is unstable because the bounded input gave us an unbounded output. So it is not Bible stable, okay? So it must be Bible stable for us to say the system is stable. Okay, go ahead, Samuel. Alozie.
Yeah, good afternoon, sir.
Very good afternoon.
You mentioned something. You mentioned that if both the inputs and the outputs are bounded, the system is stable. Yes. What if both the inputs and the outputs are unbounded?
It's not stable. That gives
It's
us,
still not stable.
yeah. So that gives us the
Okay.
next system, unstable systems.
Oh, okay, sir. Thank
Yeah,
you.
so we have stable systems, then we have unstable systems. So this example that we just have, that we just, played with here is an example of an unstable system. Yeah. So, Alozie, are we good?
Yes, sir.
Okay, so we have Okpara Wilson. Go ahead, please.
Good afternoon, sir.
Good
So my
afternoon.
question is, for this unstable system, you integrated a unit function, function, and then it gave you this ramp.
Mhm.
So are you saying that for a stable system, if you perform the same integration on it, it will still give you a unit function?
Okay, now, well, I just characterize this system to say, well, this system is an integrator. The system could be something else, okay? The system could be something else. But the idea about having a system is that it must perform an operation on the signal, okay? So just to showcase an example of an unstable system that is not Bible stable, then we just played with this, okay? But should we feed an input into this integrator and then both the input and the output have finite amplitude, then it is Bible stable. Is that clear, Alozie?
Yes, sir.
Okay. Okay, now that we have done this, I think it is time we begin the business of the day. Okay, so we've played with a lot of manipulation of signals and all of that. So let us begin to talk about LTI systems. Okay. Ehis, go ahead, please.
Sorry, the system is stable because is it because of the minus infinity as the boundary, as one of the boundaries?
No. That's not it. This is just an example of a system. So this system could be something else. It could be anything, okay? So what informs stability is this: Bible stable. It should be Bible stable, meaning the amplitude of the input should be finite as well as the amplitude of the output. That's what informs stability in this sense, system stability. Is that clear, Ahis? We can't hear Ahis. Is that clear?
You understand what you mean?
Okay, what don't you understand? Tell us, please.
Like you said that what makes it unstable is that either the output or the input is unstable.
Yes. Now, what makes the system unstable? The thing that makes the system unstable is when we do not have bounded inputs or bounded outputs. Okay? And now we are looking at the signal. What we are trying to say is that the amplitude of the signal should not extend to infinity. It's just like saying we have infinite.
Right.
That does not exist in real life. It is theoretical. We can't have infinite power. Okay? So when the amplitude extends to infinity, the system is unstable because we really won't be able to manage the analysis of that signal of the system. Is that clear, His?
Yes, sir. Yes, sir.
Okay. Elvis, your hands, I can see your hand up. Go ahead. Okay, Elvis, there's no more talking. Okay. So now let us talk about linear, let's change the color. Linear time invariant systems. Linear time invariant systems. This is the popular LTI systems. Now, we already explained that, well, for the system to be an LTI system, it has to be linear and it has to be time invariant. So meaning it obeys the principle of superposition, and also any time shift in the input should result in an equivalent time shift in the output. Then we say, well, it is a linear time invariant system. So it means that your vehicle is a linear time invariant system. Should you ignite the engine at 1 a.m., it gives you the expected response. And then if you decide to ignite the engine 2 weeks after, you get the same response. But when you now ignite the engine 2 weeks after or later, then it doesn't respond, then it means it is now beginning to become nonlinear. So what do? You want to fix it. That's what we are trying to say. So it means that the LTI system is an LTI system when these two concepts are observed: linearity and time invariant. Okay? So if that is true, remember I made mention of something, that the system also have some level of impact on the signal. Okay? So that when we talk about time shifting, we now have to talk about the time invariance. This brings about time shifting. Okay? And for us to be able to play with this time shifting in the time domain, so there's a concept that we are going to bring on board, which is convolution. Okay? So it means that for us to be able to designate this system with its parameters accurately, should a system be fed, or should a signal be fed into a system, or should a system be excited by a signal S of t, a linear time invariant system then we should have an output y of t for which the system parameter, which we are going to address as the h of t, convolves with the signal s of t, for which this system is described as having the parameter h of t, saying that it is an LTI system. So now you are going to note that continuous time systems conventionally, as you already know in your mathematics, are described using differential equations. Okay, and all of those differential equations have two basic solutions, right? Who can tell me the solution to your differential equation?
Is it general solution and particular solution?
The general solution should be a function or a combination of two solutions, the particular and homogeneous component, right? Isn't it? That's what you did when you played with differential equations. So you have the particular and the homogeneous component. Okay, now, Obara Wilson want to tell us something.
No, sir, sorry. I wanted to actually ask a question.
Okay.
Can you go over like this equation or function you just did, like the LTI stuff that you did? Like I didn't understand it.
Yeah, don't worry. You're going to understand it shortly because we've not started analyzing convolution. Okay, so we are still going to do, the impulse response and convolution analysis of the LTI system. But what we are trying to say is this. Earlier, in the previous slide, we fed a system with a signal, and then we said, well, this y of t is the same as s of t. This is what we have been playing with, because we assume that this system have just unit influence on this signal. But the bottom line is this system itself is built based on a certain model or circuitry or whatsoever, okay? Now, the system is a combination of components working together, and that system must have an impact on the signal, okay? So that moving forward, we want to begin to model the system, to align with what we should be able to conceive in practice, okay? Although it is still an abstraction, okay? And that is where this is coming from, okay? But notwithstanding, we are still going to play way with the convolution, largely because this h of t that we are saying here for the LTI system, h of t, is a property that characterizes the system, okay? This is the property that characterizes the system, okay? And it is in the time domain. Soon we'll begin to talk about transform, how to move from either time to frequency domain, which is more convenient to solve the problem, okay? And when we begin to talk about convolution, when we move from the time domain, h of t, to the frequency domain, the h of t now becomes h of s in the s domain for us to be able to resolve the Laplace transform. And then we now address this component as the system function, or better still, the transfer function. Don't worry, we are going to talk about all of this, okay? But what we are trying to say now is that once we feed this system with this signal, s of t is now going to interact with this system parameter. So the process by which it interacts with this system parameter in the time domain is what we call convolution. Now, while we are doing this in the time domain, say convolution, we are still going to talk about it in detail. But in the frequency domain, we are actually performing multiplication. So that's why it's more convenient for us to analyze these signals in the frequency domain, because we just play with, because if we want to perform the convolution operation, then we have to begin to play with some lines of integral, okay? And then for some of you, it may not be convenient because at this point, let's change this color. This expression will now be expressed in the integral as, say, y of t being the same as the integral, taking our limit, say s of t being the signal, and then this, we introduce the time delay, okay? Remember, time invariance. So it is this parameter that we now introduce the time delay such that we now have the impulse response of t minus tau dt, or yeah, you can say dt or whatsoever. Now, this now is an expanded form of this expression for the continuous time signal. But be rest assured that this system parameter is now having impact on this signal. And the time invariance of this whole operation is now accounted for by this operation, okay? And then we can now begin to analyze. So we are saying, well, this is more like the general representation of what we have here. But what we want you to understand at this point, you don't need to bore yourself with any of these complexities right now. It will become clearer as we move in the right pace. But what you should take note of at this point is that once we excite a system with a signal, the parameter that describes that system is going to convolve with that signal. That is what we are doing here. Okay? Does that make any sense, please?
Yes, sir.
Okay. Okay. So just calm down, relax. Let's just move in the right pace so we don't get things clumsy. Then if you also have some time, you can always go back to the lecture notes you have online. Then you look them up. Then if you still don't understand, then we'll address any misunderstanding in class. Is that okay? Is that okay?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, so now let's move on. Now,
Yes,
since we have this system, say S of t, serving as the excitation to the system that is described by the impulse response h of t, then we are saying that for which the system is an LTI system, we are saying that the output is such that the impulse response convolves in the time domain with the input S of t. Okay? And we already know that continuous time systems are described by differential equations. So this is the idea. We want to model a system. Okay? Now, we know what the output and the input should look like. We want to synthesize it. So what do? What we're interested in is the differential equation, because everything we are talking about right now is a function of some variable that is changing with respect to time. So I'm speaking right now, and you get to hear me with respect to time. So my speech signal can be modeled using differential equations. So anything as far as the engineering domain or science domain is concerned can be modeled using differential equations. You see an orange or an apple falling from a tree can be modeled using differential equations. The vehicle moving at a certain speed or velocity can be modeled using differential equations because certain parameter is changing with respect to time. So that is the idea. So we are now saying all of those calculus you learned because you were just you wanted to be taught how to model real life systems. So we are not trashing them. So we are coming back to the calculus, your differential equations, your differentiation, integration, and the likes. So we want to apply them now, but this time we are going to be applying them in terms of modeling a system. And this is the good news. Once you are able to develop the differential equation for the system, you can now define or describe the parameters to achieve those, to achieve the system. Say, for instance, well, we're going to get to that shortly, okay? So, or should I move so quickly, or I should just hang on a bit so that I don't overstretch, I don't overstretch your minds. Okay, well, let me just mention, so we just make to put a little to make it a little interesting. So you know that your capacitor, for instance, the current I of t is related with the voltage by C dV of t dt, right? So you now see that this is differential equation. So let's assume I have a system. Let's say a system such that I know, okay, my capacitor is XYZ value. So I know that my voltage and my current is related by this differential parameter. So it means that I can plug in a capacitor to describe, to model this behavior in my system. Does that make sense? So now I really don't know the components to put together to develop this system, but I'm running a model. Now I just arrived at a differential equation where I'm able to draw the relationship between my current and voltage. But I know my current and voltage are related by this. And there's a particular parameter here that describes this interaction. Now, your inductor also is the same, where V of t is the same as LDI of t dt. So it means that if I'm able to develop the differential equation that relates my current with my voltage in this manner, then I can actually replace whatsoever model I have with an inductor. Okay? So it means that with the differential equations, we should be able to synthesize a system and then put the circuitry together, and then we now observe the input, the output relative to the input to see if we are getting the expected response. That's one way, okay? But let us come back home. So I want you now to note that continuous time systems are described using differential equations. And from your calculus, you were told that the general solution is the sum of the particular solution and the homogeneous solution, right? Or component. Now, we are going to see something like this in the LTI system, except that in the LTI system, our general solution is a sum of the zero state response and the zero input response. So I need that to sink in, okay? Now, your zero input response is more like the natural response. I wouldn't know if you've gotten to your first order, second order transient in fundamentals of electrical engineering, but well, you'll get there. Then your zero state response is the same as the forced response. Okay. Okay. Now, for us to be able to analyze the system, so it means that our zero input response, which we have also designated as the natural response, is the output of the system when the input is set to zero. Okay? So let us wipe this. So for your LTI system, So we have that the general solution is the sum of your zero input response plus your zero state response. Okay, we have Ifeanyi. Go ahead, please.
So please, can you repeat or explain this zero input response and zero state response?
Exactly.
And
That's
no
what,
problem.
yeah, that's what I want to do now. That's what I want to do. So now I already said that the zero input response is the same as the natural response. It's not forced, okay? Natural response. So when you begin to play with your transient analysis and all this natural, there's no energy source in it. So there's nothing driving energy in the system. It's just the way it is. We just have some circuits put together and all. So one to assume that it's in a zero state, right? So what we are trying to say is that the output of the system is achieved or derived when the input is in the ground state, when the input is zero. Okay? So this is the response of the initial conditions only. Okay? So here we are considering initial conditions, right? That's why it is zero input response. Okay? Now, the second part is the zero state response, which is the same as the forced response. So from the word forced response, so it means that it has been energized. Okay? So I would say this is the output of the system when an input is applied to the system, all right? So such that the total solution will now be the sum of the zero input response and the zero state response. Is that clear? So we are going to come back to this, okay? So we are building a bit of background, we are just building that background, and so we're able to move in the right pace, okay? Is this clear?
Yes,
Yes,
sir.
sir.
Okay. Now, let us move on to the formulation of the representation itself, okay? Now we have discussed that, okay, we have one hand up.
Sir, sorry, sir.
Okay.
So for the general solution for an LTI system, if the zero input response is added with the zero state response,
It's
the
what?
final solution for the general solution LTI system, if the zero input response is added to the zero state response, are we going to get the zero state response as our final solution?
We can't get the zero state response as our final solution. The fact that we are saying where zero input response does not mean the answer is going to be zero. Well, what we are saying is that we are actually considering the analysis based on initial conditions. Now, have you done boundary value problems in mathematics or in any of the courses?
No, sir.
Okay. Well, in fundamentals of electrical engineering, thankfully, you are going to do that, okay? So that you are going to talk about natural response and forced response. That's when you begin to talk about transient analysis. I know I'm not sure I made the lecture notes on that. Maybe I'll make the lecture notes and upload them to the fundamentals of electrical engineering if I've got some time. But that's when you begin to play with that. Okay, so you want to check the response, the natural response, and the forced response. Then you want to say, okay, fine. Let's assume I have a circuit. Now, before I switch, what is going to happen So when I switch and the system is energized, what is going to happen? So we are going to get values. So the fact that it is zero input response does not mean the answer will be zero. Okay, so we are only going to analyze the system based on initial conditions, and we'll get some values. We'll get, certain, but by the time we add the responses together, then we now have a model that describes that LTI system. Is that clear?
Yes, sir. Thank you, sir.
Okay. So now we have actually talked about, all of these input output activities in the time domain. Okay. But like I mentioned earlier, in practice, it's easier for us to play with these systems in the frequency domain. So I want us to begin to make some adjustments. So we now need to make a formulation for the frequency domain representation of signals and systems. Okay. Now, for us to be able to do that, you recall that we made mention of something in our previous class, that the signal we play with in practice is a complex signal, say cos t plus j sine t. Okay? And we can represent this in the Euler form to say this is the same as epsilon jt. Okay? Where this is the Euler representation of, the complex representation. It could be in the polar form, it could be in any form, any other form. Okay? And since this signal, S of t, is a complex signal, so it means that it consists of a real component and an imaginary component. Okay? So it means that S of t is a function of, say, a real component, a sigma, plus an imaginary component, j omega. And now we know that omega is the same as 2 pi f. You played with that in physics, simple harmonic motion and the likes. You've played with all of this to know that, okay, fine. Omega is the angular frequency and it is the same as 2 pi f, right? So we know this. So if now you observe that the frequency is in the imaginary component, right? Now, if we plot this process, so we are now going to have the S domain. This is what brings us to the S domain. Okay, where this is the real part, and then this is the j omega axis. Okay, and we call this the S plane, where S is the same as sigma plus j omega. Okay, now, if this is so, then in the S plane, we can now represent our signal S of t as epsilon st in the S domain. Okay? Now, so it means that S of t in relation to the complex X plane can be designated as, as this. Now, this is very, very important. Okay? Because in the continuous time systems, or in continuous time systems rather, this function is usually referred to as the eigenfunction. This EST. It is the eigenfunction. And this eigenfunction is the input to a continuous time, linear time invariant system. So it means that once we have a linear time invariant system, the eigenfunction, EST, is the input to the system. This is a continuous time LTI, okay? Which is described as h of x, such that the output will become HEST. Now, is this clear? Is this clear? Because I need this to sink in before I'm able to progress.
No, sir.
No, sir.
Okay.
Sir, it's not clear.
Okay. Okay, so we'll take it one step at a time. Okay, Ajugo, Israel, go ahead, please.
Good afternoon, sir. So when we
We can hardly hear you.
sir, when you mean the eigenfunction, do you mean the eigenvalue?
What did you say?
I said, when you mean the eigenfunction, do you mean the eigenvalue?
No. The eigenvalue is related to the eigenfunction, but we mean the eigenfunction, not the eigenvalue. Okay, not the eigenvalue, please. Okay, so for every
Yes.
eigenfunction, there is an eigenvalue related to the eigenfunction. Okay?
Okay, yes, sir.
So this is the eigenfunction. Now, this eigenfunction is just telling us that, well, this is the input to a continuous time LTI system. And we know that the input to an LTI system is usually a complex signal. That's what we are just saying. There's nothing more. So once you hear the word eigenfunction, just know that the eigenfunction is an input to a continuous time LTI system, such that the output is a replica of the input with the exception that it is multiplied by the scaling parameter, h. So now this h should be h of x. So let us write it correctly. So that's h of x, right? H of x, because we have now moved into the into the frequency. We are beginning to move into the frequency domain, okay? Because once we analyze the explain activities, then we can pull our frequency. So because this is going to lead us to Laplace transform, then when we now consider just the j omega, then we talk about Fourier transform, okay? Now we are gradually moving into all of those activities now. Okay, now I'll just try to reemphasize a few details. Now, in our previous lecture, we explained that the signals we play with in the strict sense of it are complex signals. Hope that is clear.
Yes, sir.
Now, if they are complex signals, it means they have the even and odd components, right? I'm sure that is also clear. But you will recall that from your engineering mathematics, when you played with complex signals, you could either represent it in different formats. It could be in polar, it could be in Euler, and all of that. And we're saying, well, we can equally represent this complex signal in the Euler form. Okay, this is the Euler form, right? So meaning once we have EJT, we can decompose it to now have the real and imaginary part, isn't it?
Yes, sir.
Yeah, so meaning with EJT, I don't have to write cos t plus j sine t all the time. I just, once you see your epsilon jt, we are dealing with complex signals here, okay? Now, since we are dealing with complex signals, so it means that if we should plot on the axis, we have the imaginary component and we have the real component, right? That's what you played with in your engineering mathematics, right? Isn't it?
Yes, sir.
And then this is R, okay? And then you are able to play with all of those, and then you plot, and then you're able to convert from one activity to another. Now, the imaginary part is the same as j omega, which you placed here, while the real part is the same as sigma. Now, this just provides an interpretation of what we refer to as the X-plane analogy. Okay? Now, if this represents the S-plane analogy, so it means that S is the same as the sum of sigma and j omega. Is that clear? Is it
Yes, sir.
to this point? Fine. Now, if it is clear to this point, so it means that all of these JT activities, we can equally represent it as this also. Okay? because this is just to describe that where we are dealing with a complex signal. That is the same thing here. So meaning that in the S plane, once we replace our J with our S, then it means that we are pulling our real and imaginary component, which describes the S plane, and we are writing the same thing. Is that clear?
Yes, sir.
So we are not saying that if S of t is the same as EST, that this EST is referred to as eigenfunction. It is referred to as eigenfunction because it is the input S of t to a continuous time linear time invariant system, because EST is a continuous signal. Is that clear?
Yes, sir.
Yeah. So it means that this EST, if I don't want to write S of t, I can as well write EST. The bottom line is my ST, we have been able to identify, or better to describe it, to be a complex signal, right? And now we have been able to represent this complex signal in the Euler form. And we are saying, well, both S of t and EST are the same, and they form the input to the continuous time linear time invariant system. But, well, we can't call EST ST anymore because it is now ST. So, and as such, it is the eigenfunction. And when we now mention eigenfunction, we are now saying that this eigenfunction EST is an input to the continuous time linear time invariant system, such that the output is a replica of this input, because we have EST, save for the fact that the parameter that describes the LTI system multiplies it. So it's scaled by that parameter. Is it clear?
Yes, sir. Sorry, sir.
Go ahead, please.
Please, the eigenfunction, is it called eigenfunction because it's the input to a CT-LTI system, or any function in that form, or any, how do I put it, any expression in that form is an eigenfunction?
Okay, any expression in this form is not an eigenfunction. Okay, now I'll give you an example. EST U of t seems to be in this form, but this is not an eigenfunction because it multiplies a unit step function. So it's going to truncate a certain part of the signal, okay? And,
yes, sir.
And as such, this is going to pass just the positive half of the signal. So this expression that is of that form is not an eigenfunction because it does not give the complete interpretation of the input to the LTI system. That is the continuous linear time invariant system. Is that clear?
Yes, sir.
Okay, so Ibukun, can you tell us?
Yes, good afternoon, sir. So I wanted to clarify the part of the transformation from the time domain to the S domain, right? Are we saying that sigma, because x of t is a function of t, right? And t is the independent variable, therefore it is, it's changing. So that's where we moved from cos t plus j sine t to sigma plus j omega. Is sigma and omega a constant value? And if so, do they relate to cos t? Like, is sigma the same thing as cos t and omega the same thing as sine t?
Okay, not absolutely. So we need to get something clear here. Not absolutely. Now, here we are playing with domain representation, S domain representation, okay? Are they constant values? No. Because omega is a function of frequency, and the frequency may vary. Is that okay? So we cannot really say they are constant values. They vary depending on, certain conditions or parameters. It depends on what you are modeling, it depends on the synthesis, and it depends on a whole lot of factors. There are a whole lot of factors. Now, this is the most simplified form of representing the entire process. So in designing the actual system, they will put up all of these components to arrive at that. But what we are trying to explain here, now this is a different format, okay? Now we can equally represent the complex signal in this format, okay? In this format. Now we can equally represent in this format, right? Now we can also represent L theta. This is also a complex signal.
Okay, yeah. Yes.
In the polar form, yeah. So what we are trying to say here is that, well, this is a typical representation of the same complex signal in the S-plane. Now,
okay,
do you get that? Where we have the real and imaginary component.
Okay, so my question now is, how do we relate the representation of cos t plus j sine t to the S-plane representation of sigma plus j omega? What's the
What's the relationship?
transformation?
Yeah.
What's the relationship between the
Now,
two?
perfect. Good question. And now, what is the relationship between this representation and this representation?
Well, the theta represents the angle, and then R represents the is it the modulus, right? So the length of the signal. But in this representation, there's no R. That means R is 1. So the theta totally defines the complex signal here.
And then you're able to do conversion, right? Exactly.
Yes.
That explanation serves our purpose to the X domain. But the point is, we are drifting from the time domain to the frequency domain. So this does not cut it because we do not have a time component here anymore, but we have a frequency component. We are now explaining the complex signal in two different domains.
Okay. Well, okay. I think I understand that. It's just I'm trying to see.
So this
Does that mean the signal is changing, or
it's not
we are
changing.
just taking a different component of the signal?
No, it's the representation that is changing. This is time domain and this is frequency domain. The representation is changing because the plane in which we are representing is now different, but we are actually talking about the same thing. Okay, now when we go way into our analysis, we realize that while we are able to perform convolution here, we are performing multiplication here. So a whole lot will change, okay? We are still dealing with the same thing, but it's just that we are now going to be learning new, we're not going to, is it really new? I don't think it's new, but we are going to be learning the techniques for analysis, okay? So there are basic techniques that you now begin to learn to analyze a signal in the time domain or to analyze a signal in the frequency domain, more like algebra, okay? Yeah.
Okay.
So we have different lines of algebra for all of for these in these two domains.
Okay, I think it's clear now, but I'll still need concrete examples to hammer it in. But yeah, you can move forward. Thank you.
Yeah, we'll play with more examples. So, like I was saying, convolution in the time domain have its own mathematical representation, while multiplication in the frequency domain have its own representation. But we'll say that convolution in the time domain is equivalent to multiplication in the frequency domain. But should we perform multiplication in the time domain, we won't get the outcome of convolution. I don't know if that's clear. Is that clear?
Yes, sir.
Yes, yes.
Yeah. So that's about it. So we cannot say this is equal to this or this is equal to this. No, we can't say that because we are in two different domains right now. So while we are talking in time domain, we are talking in frequency domain here. Okay. Now, okay, we still have some time. That sounds good. Okay. Now, if this is clear, then someone made mention of eigenvalue. Okay, so let's see if we can quickly distinguish between the eigenvalue from the eigenfunction. I know you played with all of that in your mathematics, right? So there's a clear distinction. So let's assume we have the input to the LTI system, which is our eigenfunction, EST, as the excitation to the continuous time LTI system, such that the output y of t is the same as 1 over t, which is the time period, t minus t over 2 to t plus t over 2, s of tau d tau. Okay? So this is what we have. So what are we to figure out here? We want to determine the eigenvalues of this continuous time LTI system. If this is the eigenfunction, then what is the eigenvalue? Or what are the eigenvalues? Okay? So now, it means that if s of t is the same as this, then it means that s of tau will be the same as es tau. Okay? And we already know that this is fed into the system such that our y of t is the same as 1 over t integral t minus t over 2, t plus t over 2, epsilon s tau d tau. So once we integrate this, so it means that, excuse me, we're going to have 1 over t into bracket with respect to tau. So that will be es tau over s, right? So t minus t over 2 to t plus t over 2 plus t over 2. Those are the limits, okay? So we can bring that out. So 1 over st, if we bring out the s, so es tau, right? Then we have the limits t minus t over 2 to t plus t over 2. So once we expand this, so that will be 1 over st into bracket epsilon s t plus t over 2 minus epsilon s t minus t over 2, isn't it? So now we can also expand this. So that will be 1 over st into bracket e st. Now, so recall your logarithm, laws of indices, and the likes, right? So that will be est epsilon st over 2 minus e st epsilon minus st over 2, right? So from this, we now have 1 over st into bracket e st over 2 minus e minus st over 2 est. Okay? So technically, this is the same as lambda, so that we now have lambda est, for which lambda equal to 1 over st into bracket E st over 2 minus E minus st over 2 is the eigenvalue. Why? So that's why. Why this is the eigenfunction. So it means that this system operates on this such that this is now the same as h of s, right? Which is the parameter that describes the system. But the bottom line is it's an LTI system because what we gave as the input, we also have it at the output. Is that clear?
Sir.
Yes.
Okay. Now, if that is clear, I think we can move on. Okay. Now, we've been able to establish that, well, the continuous time, linear time invariant system can be represented using differential equations, okay? So we want to model LTI systems. Okay, someone's hand, okay, go ahead, please, Ibuku.
Okay, so the math is clear, but you kept saying T, T, T. I believe there are like 3 different T's here, so I'd like to know the meaning of the T's. I think one is the capital T, that represents the period, right?
That's the time period. This is time period. Why this is your time, which is the signal is a function of time, right? That's all. While
Okay.
S is the S-plane representation.
Okay, so that means okay, so are we saying all linear time invariant systems are periodic take periodic inputs?
We have not said so.
Okay. Okay. What's the definition of the time period in this context?
Okay, what's the definition of the time period? Now, what is time period?
The duration of a single oscillation.
Okay, so how many oscillations do we have in this signal?
I don't know.
Exactly. Now, okay, let me put it in a more technical format. How many harmonics do we have here?
1.
Who said?
I don't know. Actually, I'm just trying to.
Exactly. So you want to plot this. So you go plot this signal on your MATLAB. And then let us see the graph. Then we'll be able to tell. Okay? So this is what you want to plot, right? Go plot this, then assign values to it. Then we should be able to tell. Okay? Because what you should take note of, we did not say that we did not say this is the fundamental time period. Now, if we had said this is the fundamental time period, it would have been T naught, then you'll be talking periodic. Okay? Because this is the smallest value of this, right? Is that clear, Ibuku? From the definition, yeah?
Yes.
Exactly. So it means that we have other time periods here. So you can't just confirm to say, so we must have to play with some harmonics, whichever way. So meaning we have F naughts, 2 F naughts, 3 F naughts, probably all the way. Yeah? Clear?
Okay, so that part is clear. Thank you.
So we now need to figure out what is T naught for us to be able to place T. Is that clear?
Yes, sir.
Okay, so we have Ebube Chukwu.
Yes, sir. Thank you, sir. Sir, I don't understand how we are using tau and t interchangeably.
Okay, okay. How we are using tau and t interchangeably. Perfect. We'll resolve that now. Then let's take the other guy, Habib. Let's see if it's the same.
Yes, thank you, sir. I wanted to ask why for the integration you made the limit t minus capital T over 2 and t plus capital T over 2.
It's just given.
What if I were to use the limit, sir?
It was given, so it could be any limit.
Sir?
Did you get that?
Okay, so you come in, okay. Yes, I get that. I got that, sir. Thank you, sir.
Okay. So why did we place tau? Because that's what we have at the output. Okay. Now, when we begin to play with convolution, you now see why we have to do that, because the system already operated on it, so we cannot retain this, so we have to switch. So at what point do we switch from this to this? So this is input representation, and this is output representation. Okay, so with this,
Yes, sir.
with this, we are able to introduce a time shifting, whether it is delay or advance. Okay, yeah. So we are going to be seeing that more often. But in this simple analogy, we just had to play with it because someone was asking, is the eigenfunction the same as the eigenvalue? So we just wanted to clarify that, to play with this. But notwithstanding the limits, they are not statutory. It could be anything. Then the order, fine. We've also interacted or played with that. Yeah. So any other question for now? Okay. Wow. And we have quite a lot I was going to still talk about today. So probably we'll move this to our next class, because we will need a little time to push it further. So but the bottom line is we've been able to play with a few things, and I did make mention. Okay, so we have average of 8 minutes, so let me just play with this part, and that'll be a good place to stop. So in modeling LTI systems, so let's look at modeling LTI systems. So, but you should take note that so far we've been able to mention one representation, one way of representing LTI systems using differential equations. We could also represent differential equations using the graphical method. We could also represent the LTI systems using a state space representation. Okay, so so that's just off this anyway. Let's just so far we've mentioned differential equation representation. Now we could use a graphical method, right? We'll play with that probably next time, graphical method. Now we could also do state space representation, right? Well, this is really interesting because we are able to do some computer programming here, programming, so that we now come up with a matrix representation, okay? And with that, there's a system matrix. So once we're able to pull the system matrix in the matrix format, then with this, we can detect, or better still, estimate the stability of the system. So that's very key. Okay, those of you in power systems and even in other fields, stability is key. Okay, we don't want to design systems that are not stable. So let's assume you built a robotic system that is supposed to perform useful operation, and then it becomes destructive. We don't want that. Okay, so we want systems that are stable, that will respond to the input we feed to it, and not act otherwise. Okay, so you have a driverless car, so suddenly you got into it, and well, you program it, all of a sudden it takes you to the ocean and runs you over and lock the doors. We don't want that, okay? So I know security is one big issue when we talk about technology, but we also want to develop stable systems. So we've talked about differential equations, then we have the graphical method, then we also talk about state space. But unfortunately, we won't be able to play with all of those today because of time. But let's just look at basic modeling, okay, of LTI systems from your circuit perspective, okay? So let's look up things from the circuit perspective, and I think that should be a good place to start. So I already mentioned one. So let's say your linear elements. So we already know they are linear elements, but can we really classify them as LTI systems? So at what point do they fail to be LTI systems? So let's say V is the same as R I of T, right? This is your resistor, right? When we model your resistor, okay? So within power limitations, the resistor is a linear element, okay? But there's something that happens. Now, this resistor with resistance R will cease to be a linear system if we apply a very large voltage. Because once we do that, it's going to burn out. And then this linear relationship will not hold. So in practice, it will cease to be linear under certain operating conditions. That's what I'm trying to say. Now, let us also look at another linear element, your capacitor. Okay? So we have the charge being the same as the capacitance times the voltage value, right? Such that I of t is the same as C dV of t dt, right? So now, if we consider saturation, the capacitor is not linear, okay? But if we neglect saturation, then the charge stored in a capacitor is related to the voltage by a linear relationship, okay? So now saturation, so here, large voltage could trigger nonlinearity, right? Now, in this case, saturation could also trigger nonlinearity. Now, how about inductor? But fine, in your second analysis, you are made to understand these are linear elements, okay? Now, the flux, as psi of t, is the same as the inductance times the current value, so that V of t is the same as LDI of t dt, right? Now, the flux generated by the inductor is related to the current via this linear relationship, okay? And should we also consider saturation and some other activities, then this system will not be linear, okay? So one thing you will observe is that all of these elements here have some differential relationship, okay? So we can classify them as differential equations, okay? And I think that's one good place for us to stop right now. So we could pick up some other things in our next class. So any question, please? Any question, please? Ebubechukwu. Ibukun, go ahead, please. Any question for now?
Okay, so just I don't want to. Okay, so you are done with the class for today.
Yes, yeah, we are done. We just have 2 minutes, so our time will be up.
Yeah, so in the previous slide, in the previous explaining you were doing, right? You converted x of t, then the integral representation you gave, like what was the like what's the definition for the integral representation? I don't know if my question is clear.
Okay,
Like,
well, we just gave an output to say, well, this is the output we've got based on the system response. It's just for analogy. Let's put it that way. So we have not got into convolution yet, if that's what you intend. Okay.
no, okay, so what I'm trying to say is that particular representation 1 over t, the integral from t minus half to t plus half of the other ones, like that's expression. What's the
that's the effect, that's the import of the system. That's what we are trying to say. Now, that system is characterized by that parameter. I don't know if you get
Okay,
what
so
I mean.
you could have another system characterized by another parameter.
Exactly. It depends on what you want to achieve. The system you use for the design of your vehicle, your automobile, is different from the system you use to design your aeroplane.
So that means in the previous example, we could have equally said maybe x of t is equal to the maybe 1 over 2t, the integral from, let's say, t minus 1 over 3 to t plus 2 over. So we could change all those things.
Now, when we change that, we will now synthesize. Now, you see that the eigenvalue is the system response itself, defines the transfer function of the system. The h of s, that's lambda. Okay?
That's the property that that's property that describes that system.
That system, yeah. So if we should change that, so remember, if you recall in our first lecture or so, we mentioned that when you have an idea of the input and the output, you could synthesize the system. Meaning you could come up with the parameter that describes the system when we try to resolve the synthesis problem. You know, conventionally, we do more of analysis, right, in class, because we have the input, we know the system, then we want to get the response. We want to see how the output will look like, right? But now in that problem, we gave you both the input and the output, then you now have to give us what the system.
Okay, that was how we found the lambda.
Exactly. And that eigenvalue gave us the property of that system.
So is lambda the same thing as h of t
Exactly.
or h of s?
H of x.
Lambda
H of
is
s.
the
Yeah.
Okay, so lambda is h of t.
H of s, not
or
H.
h of s.
Because we are playing in the frequency domain, in the S plane. Yeah. So things will get
Okay.
clearer as we progress. Okay, we are 2 minutes ahead of time. So sorry for taking 2 minutes of your time, and hope to see you next class. Bye for now.